Hey, chemistry team! It's your chemistry coach coming at you. We're going to do a little journey into redox reactions, which, if you're in first semester general chemistry or intro chemistry, is the bane to all existence, right? I found one of the hardest things for students to really, truly grasp. Um, Coming from the first semester of general chemistry is redox reactions and then ionic equations as well. That sends them in a hizzy, whatever hizzy is. I don't know what that is. And if you're in second semester general chemistry, this is good review if you're heading into electrochemistry, because that's going to be all about utilizing and manipulating redox reactions. So let's do a quick little intro and overview on some of the terminology, look at oxidation numbers, review that a little bit. There's a lot to it. And again, this is one of the big kahunas of types of reactions that we'll see in chemistry, right? We had precipitation, acid-base or neutralization reactions, redox reactions is right up there with those big three. All right, so redox, of course, is a contraction. For the RED is for reduction, the OX is oxidation, sticking together, and what do you get? Redox. So that stands for reduction with oxidation. It's the combination of the two. You can't really have one without the other. Let's take a look at what those terms mean. And again, a redox reaction, if you really want the essence of it, it just means electron transfer. Boink! Electrons are going from one species to another. That's all that's happening. Not much different from acid-base reactions, where it's just a proton going boink from the acid to the base. I'll compare and contrast acid-base with redox. Lots of parallels between these two, except for the products you get. We'll find out with acid-base reactions, it's pretty easy to predict what products you're going to get and balance those equations. For redox reactions, not so easy to predict your products, sometimes impossible at the level we're at, and balancing some of them, especially if they're an aqueous solution, good luck with that. All right, we're going to need some special rules for that. Here we go. So reduction, of course, means to go down. Oxidation, not so intuitively obvious, to go up. Depends if you're an organic chemist versus a general chemist. We look at oxidation a little bit differently. But as a general chemist, we look at reduction and oxidation as electron gain or electron loss, because electrons are negatively charged. So if I lose an electron, I'm losing a negative charge. If I gain an electron, I'm gaining a negative charge. Think of it that way. Problem is, if you don't remember electrons are negative, everything's backwards, right? Hey, I'm gaining a particle. Yay, I'm going up. No. It's a negative particle. Your charge just went down. So reduction. It means you have a reduction or a decrease in your oxidation number. So some atom, some element, whether it's by itself or in a compound or some species, gains an electron, meaning it gains a negative particle, so its oxidation number drops. So maybe it was a 5, and if it gains an electron, it goes to a 4. If it was a 0 and it gains an electron, it goes to -1. If it was a -3, gains an electron, goes to -4. If it gains 3 electrons, it can go from 0 to -3, or 5 to 2, or -3 to -6. Doesn't matter how many you gain, as long as it's 1 or more electrons. So a decrease in oxidation number on a particular element, atom of an element, due to gain of 1 or more electrons. And the exact opposite of that is oxidation. So if reduction means to go down, oxidation means to go up. So that's an increase in oxidation number due to a loss of 1 or more electrons. So if I have an oxidation number of 1 and I lose an electron, I lose a negative particle, I just went up to 2. I went from 1 to 2, went up. That's oxidation in general chemistry. If I was at a -2 and I lose an electron, I go to -1. So that still is going up, even though it's in negative numbers. My brain, right? It still is going up. It's oxidizing. So it doesn't matter where they start at. It could start as a positive oxidation number, 0 or negative. As long as it's going down or up is reduction or oxidation. And if you need some of these little acronyms here, I've seen oil rig, I've seen Leo-Gur, I've seen a whole bunch of different ones. Whatever works for you. I personally don't use those. I just remember either I'm gaining a negative particle or losing, 1 or more negative particles. And reduction is going down, oxidation is going up. But I've seen oil rig. I remember learning this when I was in undergrad school. Oxidation involves loss, and reduction involves gain, right, of electrons, of course. And with Leo-Gur, loss of electrons is oxidation. Gain of electrons is reduction. Oh, however you need to remember it. This professor doesn't care. All right, let's compare acid-base reactions to redox reactions, and we'll get into some definitions. All right, let's try to look at redox in comparison to acid-base reactions or neutralization reactions, which hopefully you got a good gut level feeling for. Right? With acid-base reactions, which we looked at a while ago, forming products, of course, water plus a salt, but the products aren't important at this case. We're trying to identify what's the acid, what's the base, and in redox reactions, what's called the reducing agent, what's called the oxidizing agent. So in acid-base, if you remember, right, we looked at the Bronsted-Lowry model. Acids donate the proton, the H+, right? So we can write this as the proton donor, and the base is the proton taker or acceptor, right? Weak bases tend to be more proton acceptors. I don't really want it, but okay. Where strong bases are proton takers. I'm going to take your H+ whether you want it or not, right? So we looked at acid-base strength. But let's look at it in the same view, right? An acid-base reaction is a proton transfer from the acid to the base. Well, if we look exactly the same way, a redox reaction is an electron transfer from the reducing agent to the oxidizing agent. How does that work out? So the reducing agent takes the place of the acid, and the oxidizing agent takes the place of the base, right? So a reducing agent is giving one or more electrons. Now, if a reducing agent gives an electron to the oxidizing agent has an element that accepts that electron and gets reduced. So the reducing agent causes something else to be reduced by donating one or more electrons. The oxidizing agent you can think of as an electron acceptor or electron taker. This is the species that causes oxidation, right? So if an oxidizing agent takes an electron away from another species, it takes away a negative particle and causes that species to be oxidized. So this is where it gets weird. The element in the reducing agent gets oxidized. The element in the oxidizing agent gets reduced. So the oxidizing agent's the entire species, usually a reactant, right? That is taking an electron from something else, which causes an element in the oxidizing agent to get reduced. The reducing agent donates the electron to the oxidizing agent, so the reducing agent's the entire species. And the element in that lost the electron, it was the electron source, gets oxidized because it lost the electron. Whoa! Go have something to drink real quick. All right, but you see the parallel. Acid is to the reducing agent, like base is to the oxidizing agent. Reminds me of very bad SAT days, right? I was like, what's the opposite meaning of this word? And here's your 5 choices. And I've never seen that word before or any of those 5 words in the 5 choices. I'm like, it doesn't make any sense. Not a big fan of that. Here we go. Now the products for acid-base reactions, the salt and the water is pretty easy to predict. Trying to predict products and redox reactions, right? So you might need a redox table. Not necessary if it's out of water sometimes, but if it's occurring in solution, a lot of times we're going to need a redox table to predict our products. It can get a little dicey sometimes, but it just gives you a feel for some terminology. So whenever I say reducing agent, you're thinking that's the electron source, the electron donor, just like an acid is a proton donor. If I say oxidizing agent, that's what's taking the electrons, right? A lot like a base takes a proton. All right, let's take a look at some examples. Let's start it off with something simple. We'll keep things out of aqueous solution at this point, and that's pretty much the extent of what you do in first semester general chemistry and introductory chemistry classes. When you get to second semester, a lot of times you get into some crazy aqueous phase stuff. Actually, depending where you go to college, you might get into that in first semester as well. I know we do at the college I teach at, so we get pretty heavy into redox reactions, and aqueous solution gets kind of weird. So this would be one. Obviously, nothing is in the aqueous phase here, no water. Pretty easy to predict your products in that scenario. So your typical synthesis or addition reaction is redox. Same with a lot of decomposition reactions tend to be redox. Combustion reactions tend to be redox. And you can tell it's redox based on the fact that there's a change in oxidation numbers. All right? So we have a change in oxidation number values. That is the number one way you can tell if somebody says, hey, was this reaction a redox reaction? Look at the oxidation numbers of the elements on the reactant side, left-hand side of the arrow, versus the oxidation numbers of the elements on the product side, the right-hand side of the arrow. If they changed, it's a redox reaction. If they're all the same, it wasn't a redox reaction. Like a precipitation or acid-base, typically they don't change, right? That's why they're separate categories. And if you don't remember oxidation numbers, go review that from first semester general chemistry. That's always the first step. If you screw that up, that's your electron accounting. You're toast. Toast, as they say in Minnesota. Here we go. In this case, the states aren't going to matter. The coefficients are not going to matter. The coefficient has nothing to do with the oxidation number. But always, always, always get the oxidation number of every species first, because how would you know if it's going up or down, whether electrons are being gained or lost? So we need to do that to know what our reducing and oxidizing agents are. So this is typically how I'll put it on an exam. I'll give you a reaction. I'll say, hey, what atoms were reduced, right, going from reactants to products? What atoms are oxidized, going reactants to products? What species, which reactant, the entire species, was your reducing agent? And which reactant, the entire species, was the oxidizing agent? All right, here we go. Let's take a look at our oxidation numbers. Now remember the rules, right? Elements are always going to be 0, right? So magnesium solid, the same number of electrons as protons, so that has an oxidation number of 0, all of them. Same with each oxygen atom in the diatomic oxygen molecule. Those are all going to have oxidation numbers of 0. Now here you see the oxygen's in a compound, magnesium's in a compound. It's highly unlikely it's going to be a 0. Well, you should be able to know if you form an ion. If I say, hey, what is the formula, the chemical formula for the ionic compound magnesium oxide, you look at your periodic table and go, well, magnesium's in group 2. Alkaline earth metals always form a +2 because they lose 2 electrons. Oxygen is 2 away from the noble gas, forms a 2-. So the magnesium is always a +2 in a compound. So call that a type 1 metal. It only forms 1 charge. Charge is a fancy way of saying oxidation number, right? But it deals only with ions. The oxygen in this case must be a -2. So +2 plus -2 gives you a net 0. Remember, compounds have to be neutral. And the sum of the oxidation numbers must equal the overall charge of that species. So if you have a polyatomic ion, like the phosphate ion, the phosphorus plus the 4 oxygens all added together better equal -3. That's all review. If what I'm saying right now, you just hear, go review oxidation numbers. Right? That's an indication. If you just hear, you need to go review that. All right. So here we go. If you don't do this, the oxidation numbers, or you get that wrong, the rest of this is toast. Right? These are my oxidation numbers. Now, let's take a look. One of them must go in a redox reaction. One must go up, one must go down. I know this is a redox reaction because they changed. Boom, it's a redox, baby. The magnesium went from a 0 to a 2. It went up, means it was oxidized. The oxygen atoms went from a 0 to a -2. Each oxygen atom in there, right? We happen to have 2 oxygen, or moles of oxygen if you think of it that way. So which one went down? Oxygen went from a 0 to a 2. So the oxygen atoms, and they went from 0 to -2, right? They went down. They were reduced, went down. Oxidized was the magnesium atoms, and they started at 0 on the left-hand side and ended up as a +2 on the right-hand side. So initially they're a 0, finally they're a +2. They went up, that's oxidized. So the magnesium atoms were oxidized, the oxygen atoms were reduced. All right? Reducing agent is the reactant, the whole species. I like to include the state just to make sure I write the whole species. That caused something to be reduced. So what was reduced? The oxygen atoms were reduced. These were reduced, which means to be reduced, they had to gain electrons, which came from magnesium. And if we looked at it down at the atomic level, each magnesium atom is losing 2 electrons. Each oxygen atom is gaining 2 electrons, right? That's why we have 2 magnesiums. Each one is giving 2, each oxygen's gaining 2. It has to be a sum The number of electrons lost has to equal the number of electrons gained. That would be pretty weird. You can't gain more than there were to start with. That would be weird. So the oxidizing agent caused oxidation. Well, what caused the oxygen to be reduced? Oh, the magnesium solid. Right? I like to do the entire species. And that may be different for different professors that you have. But I like to say my reducing agent is the entire species. So sometimes you'll see this. You'll see him put reducer here. That's my that's your short-term lingo, your slang language. Instead of saying reducing agent, you just go as the reducer. Right? Now, what was oxidized? The magnesium atoms were oxidized. What caused it to be oxidized by taking electrons? The oxygen gas. So that is your oxidizing agent. And I like to write the entire species there for my reducing agents and oxidizing agents. And another way we could say is that's our oxidizer. And you can see how organic chemists tend to think of that. Oxidation tends to be adding oxygen to something, which makes a lot more sense. But to us, oxidizers are electron takers. So see the difference? There's my reducing agent or reducer, oxidizing agent, oxidizer. You can see which atoms went up and down. You want to be able to do that. And this is all just basic review stuff, nothing hopefully terribly new. Right? So get a chance to practice some of those in the homeworks and whatnot. I'm going to do in another video, I'm going to advance this a little bit to first semester and second semester general chemistry. What if you have reactions in aqueous solution? Predicting the products. Here we could predict the product because we know magnesium's a +2. We know the oxygen's a -2 in ionic compounds. Same charge, right? Same number but opposite, +2, -2. They go together in a 1-to-1 ratio. And then you balance it. Easy peasy. But in aqueous solution, that's incredibly challenging. We're going to use what's called a redox table to predict our products. Not every professor you get will make you predict the products. Sometimes they'll just give them to you. But I'll do a brief video just overviewing how to predict your products for a redox reaction in aqueous solution. And then probably on a third video, I'll show you how to balance equations in aqueous solution if they're redox. Very challenging. You can't just do it by inspection. Here we can just inspect it, right? So if I didn't have it, I'd go, well, 2 oxygens, put a 2 here, 2 magnesium. You can balance ones outside of aqueous solution by inspection, but not in. If you see AQs, don't even try to balance it without what we're going to call the half reaction method. So this will probably be a 3-video series just on basics of redox. Enjoy your intro.